Hello and welcome to lectures on state space approach to control system analysis and design. The lectures in the previous week and this week are on case study of a nuclear reactor. Specifically, we are concerned with the control of neutron density, which is proportional to nuclear reactor power, by various methods which we came across in the course. In the last week, we concentrated upon development of a nonlinear model, the linearization of the model around a steady state of the nuclear reactor, and the design of output feedback controller. Design of state feedback and the observer that I am not considering. In this week, I am considering in two lecture videos the application of periodic output feedback to the control of power level or neutron density in a nuclear reactor, and thereafter fast output sampling method is also being applied for the same problem. So before that, we had considered the design of a simple linear output feedback control. Now let us go ahead with the periodic output feedback control of neutron density in a nuclear reactor. And as I said, neutron density is a quantity proportional to nuclear power. So control of neutron density in a reactor core or control of reactor power are the same things for a control engineer. Now, in periodic output feedback control, the control signal is generated in this manner. You may recall the control signal U over a time t is given as KL times YKT, where YKT is the sample of output at kth time instant, and this T is in the range KT plus L delta to KT plus L plus 1 delta. Now, if you recall, T is a large time interval. This is instant KT and this is the instant K plus 1T. And these are the instants where we are taking samples of output. So this is the instant where we have collected the sample YKT. At this point, we will be collecting the sample YK plus 1T. Based upon these samples, we have divided this into n-1 small interval, each of width delta. The time duration between these sub-intervals is delta, and delta is t by n. So one large time interval t, at which regular samples of output are collected, is divided into n sub-intervals of time, each of duration delta. And at these instants, delta, at KT, at KT plus delta, at KT plus 2 delta, and so on, the input is updated through the gain KL. So the gains are K0, K1, etc. up to Kn minus 1. And at any lth instant, it is Kl. And then we have seen that these gains are periodic, so KL plus N will be equal to KL. So this is the salient points, a recall of those salient points as regards the periodic output feedback control. We proceed ahead. We have in the preceding lectures obtained the mathematical model of nuclear reactor, which was nonlinear, and it was linearized to obtain these 5 linear differential equations of first order each, and also one accompanying equation, because this delta VR is the output and delta VR bar is the state. So this one. We had one more differential equation relating rho and the control rod height h. However, we have substituted it in terms of h or delta h here. So that equation is indirectly brought here. So we have this set of state equations, differential equations, based on which we have also obtained the standard state space model of the nuclear reactor by defining these state variables: the neutron density proportional to power, the delayed neutron precursors concentration, the linear amplifier voltage, the state which essentially gives the linear rate voltage, and the control rod height delta H. Of course, these are incremental changes in these quantities relative to the value of these quantities at the steady state. Now, one thing which I forgot to mention in the lecture when I was telling about the development of nonlinear model of the nuclear reactor is that a nuclear reactor is a complex system as far as its instrumentation is concerned. So the neutron flux density in the reactor is at least about 10 to the power 6 to 10 to the power 8 decades, 6 to 8 decades, or by a factor of 10 to the power 6 to 10 to the power 8, it is less than the neutron density at the full power level. So means that the neutron flux density measurement has to be carried over about 8 decades or minimum 6 decades. This is an enormous range, and this enormous range is not possible to manage by a single set of instrumentation and amplifier. So for measurement of neutron density in a nuclear reactor, we have low power measurement or logarithmic range measurement, we have intermediate power or intermediate range measurement, and we have normal power measurement. So this normal power measurement is typically above 1% full power, and intermediate range will be from about 2 decades below this, so from about 10 to the power minus 2 to about maybe 5% or 10%, and low power range is even below this, so up to something like 10 power minus 2 and below. So when we developed this model and linearized it, we considered only 2 measurements: the linear signal, which is proportional to the neutron density, and the rate of change of neutron density. So linear and linear rate, linear neutron density or linear power and linear rate, and these are done in the normal power design. So the kind of reactor model we are considering as a case study is control of nuclear reactor in power design, in normal power range. In the low power range, these signals are respectively the log n and rate of change of log n. These signals are used in case of low power, and in intermediate range, low power as well as the normal power instrumentation is used. So the things are little more complicated as far as the control in the low power and intermediate range is considered. Principles remain the same, however, the system has to be designed considering that instrumentation in that range. So this is some point that has to be remembered, meaning that the nuclear reactor control which we are considering in the normal power regime is not necessarily valid in the intermediate range and the low power range. Let us proceed ahead. So this is the standard state space model of the nuclear reactor along with state equation and the output equation. These are the state and output quantity, and this is the input quantity, which is the voltage applied to the control rod. These are the expressions for A, B and C. They are in terms of neutronic parameters, that gain constants of amplifier, and this reactivity, that conversion, that how the height is related to reactivity. This is that. This is also pertaining to the rate amplifier, and the time constants also pertain to the linear and rate amplifiers. So these are the A, B and C matrices characterizing the state space model of the system. And for that continuous time system, x dot equal to ax plus bu, y equal to cx, we proved the controllability and observability analytically, and we also showed through the rank test by substituting the numerical values of various parameters and the constants. That we did. So we expect that the discrete time system corresponding to that continuous time system will also be controllable and observable, especially because we will be choosing the sampling time, etc., such that we don't encounter any complex eigenvalues, and so those results will be extendable. However, before taking up the controller design or observable design task based on discrete time system corresponding to the continuous time system, as a matter of safety, one should always proceed first by checking the controllability and observability of the system. So here also this has been done, although not specifically mentioned in the slides here. Now, as we can recall, in the periodic output feedback design, the output is sampled at larger intervals of time, which is denoted by t here, and the value is assumed to be 1 second. And the system, I mean the discrete time system, corresponding to the sampling at 1 second sampling interval will be given by this expression: xk plus 1 is phi xk plus gamma uk, and yk is cxk. Now here this phi and this gamma, they are denoted respectively by phi t and gamma t. They have been obtained for the reactor, and they are like this: phi t is this and gamma t is this, and c is anyway, it is same c which is there for continuous time system. So we have considered to obtain the output samples every 1 second, and we have obtained the corresponding discrete time model of the continuous time nuclear reactor system. Because the system has order n, and as we have proved the controllability, we know that the controllability index of the system, which we denoted by mu, is 5. We know this, and n has to be selected in the periodic output feedback control greater than or equal to mu. So we first consider n equal to 5. And because delta is t by n, so it is 1 by 5, and so it is 0.2 second. So there are 5 sub-intervals in one output sampling interval, and these delta instants we will be updating the input to the system. So we obtain phi delta corresponding gamma delta. So the discrete time system corresponding to the sampling at the rate of 1 by 0.2 hertz or 5 hertz will be given by this phi delta and gamma delta. It is obtained. Now once we obtained phi t, gamma t and phi delta, gamma delta, now the next step is to obtain one output injection gain, G. This can be obtained by any of the control design methods, either by pole placement or by LQR. Here we consider pole placement, and we obtain G to have these pole locations. One here, one at -0.5, one at -0.12, one at almost at the origin of the Z plane. So these are in the Z plane. This is the imaginary Z, this is the real Z, and this is the unit circle of radius 1. This is, you can see, this is very close to the periphery. So somewhere here and here, this is one pair. The one is at -0.5 here, one at -0.12 and one at origin. So with this G, the system phi t plus Gc is stable, and as such I have not considered any specific criterion for the reactor control, only the stability has been in my mind. So with that I have taken these pole locations. Of course, another factor which was there in my mind while selecting these pole location, that resulting G should not have very large elements, because if G has large elements, then periodic output feedback gain K will also have probably the large elements, and the large elements will drive the controller to saturation, as we know. So that has been another factor into my mind in selection of pole locations or the corresponding G. Anyway, for these pole locations, for the system given by phi t, gamma t, we obtain the closed loop poles of phi t Gc here, and this is the G. This is the G matrix for the system. Now once G is there, then next exercise is very simple. We have to solve gamma k equal to G, and this gamma, please recall, it is gamma delta, phi delta, gamma delta, phi delta square gamma delta, phi delta cube gamma delta, and phi delta power 4 gamma delta. So gamma, phi square gamma, etc. up to phi n minus 1 gamma, n is 5, so we stop at phi delta power 4, and we obtain the columns of gamma like this. Now because the system is controllable, so we will get inverse of gamma, and so K is simply gamma inverse G. This is bold gamma, this one, and thereby we obtain K equal to this, and we call it K1. Now you can see, even though the elements of G are small, see here, this is the largest one, minus 4.2. Even with that, the elements of K are quite large. See, one is here, 73, quite large. So we look for some design in which the gains are small. Although it doesn't represent mathematically a concern, but in practical implementation, large gains means even for a small error, they will generate large control signal, and sometimes they will drive the control signal to saturation value. So anyway, for this, for n equal to 5, we solve for k and we get this k. We also obtain one alternative design by selecting n equal to 8. So for n equal to 8, delta will be 1 second by 8, which is 0.125 second. So for this one, we again obtain phi delta, gamma delta system. For this, delta equal to 0.125. And we assemble gamma. Now gamma will go up to phi delta power 7 into gamma delta. Last one will be gamma delta. Because n is 8, so it will be gamma delta, phi delta, gamma delta, and so on up to phi delta power 7 gamma delta. We obtain that gamma. And now, because there are 8 elements to be solved for k, we have to select 3 of them, and I have selected these values, the same values. Actually, different values would have led to a better design, but just for the sake of demonstration, 3 of the elements have been selected. One needs to solve it several times, and one needs to do so that this, you see, the values are very large here, minus 5 to 5, very large value. At least 10 times lower they would have been. It would have been a better design. But I have purposely kept large value just to see what is the impact, just to be able to compare that when k values are large, gain values are large, what is the problem, why they should be small. Just to emphasize that point, I have taken this bad design. Even though the system will be stable for this k, however, the transient response will reflect some things which is of concern. We'll see that soon. So we obtain this design in which the periodic output feedback gain are K2, and these are 8 gains. Proceed ahead. We do the system simulation first for gain K1, in which we had n equal to 5. Controllability index is 5, so we selected n just equal to 5, and corresponding periodic output feedback gain k is k1, and we simulate this. Now, in fact, I will like to go ahead a few slides where I have shown the control over a zoomed portion. See here, the transient considered is system is initially at steady state at t equal to 0. At that time, a disturbance is injected at the control input, which is of 0.25 volts magnitude, and it is kept there for 1 second. This is 1 second, and thereafter it is brought to 0, and of course up to 5 seconds the closed loop control, that is loop is not closed, so system is autonomous up to 5 seconds in this range. So it is affected by applying the disturbance at input terminals, and it is allowed to remain autonomous up to 5 seconds, and at 5 seconds that loop is closed. And the control loop, of course, consists of a periodic output feedback control. So essentially it's like this. This is the input, this is the system, this is the where we are taking sample of output. Now this is coming through various sets of gain, K0, K1, etc. up to K5, K4, because there are 5 samples. And we were supposed to close the loop like this. So we have to select either of these, either this, like that, like this. Hope you remember this diagram. So at one time it is here, delta seconds later the switch is here, and so on. At the last moment it is here, again it goes back to that location. However, we are not closing this loop till 5 seconds. This switch closes only at t equal to 5. So even though the control signal is being calculated, it is not being implemented. The loop is not closed for 5 seconds. Thereafter the loop is being closed, and so the control action happens. Let us go back. So now if we see control signal variation over a time of interest in which the system variables come to equilibrium point or near to the equilibrium point, which is typically close to 100 seconds, we see that input varies like this. Sometimes it was minus 0.8 volt, and on the positive side it is about 0.3 volts. So not much. It can vary up to plus minus 10 volts actually. Of course, also the disturbance is small. This is how the input signal varied, and because the control rod position dH by dt is equal to some constant k, I don't remember the subscript, into, I think it was km into the input u, which is the voltage V here. So this is just a simple integration of this voltage profile which appears here in this plot, and we get this. As the control signal was constant for 1 second, the control rod height kept increasing with time. This is with the slope. Then the control signal was 0, so the control rod height remained constant, and no signal was being given, so it remains there, control rod remains there. And then at t equal to 5 seconds, controller is switched on, it is brought in the loop, and thereafter the controller starts correcting, and so the system, as far as the control rod height goes, it undergoes this transient in which the control rod height goes to negative side by 2%, 2 units. And eventually, of course, the system comes to stability as shown by the control rod position. We see some other variables, the change in neutron density. Neutron density was at a steady state here, and relative to that we are seeing delta eta is eta minus eta at t equal to 0. So up to 5 seconds, when the system was not being controlled, the neutron density started deviating and then remained deviating. In fact, it grew with time because the system is unstable without a controller in the loop. It grew with time, and this is where at 5 seconds, when the controller was brought in the loop, then the control action has started correcting, and you can see that the negative side neutron density is very small. Actually, neutron density is not negative, it is below eta 0 by this small amount. So the system corrects the neutron density without much of the undershoot. That is the point to be noted. And of course, the time in which the signal, this neutron density is brought to the equilibrium is quite large, of the order of 70 to 80 seconds. The same thing is also reflected by plot of that linear voltage. This is actually delta Vn, which is Vn minus Vn at t equal to 0, the steady state value. And this profile is identical to the neutron density profile. However, because the amplifier has a small time constant, this signal is slightly smoothened, and it is also lagging a bit. We see the rate during that first 5 seconds, the rate kept high, and of course it was corrected as time grew in time. So in this manner, the system has been controlled and brought to the equilibrium by periodic output feedback controller. Now, just to convey one more point as regards the periodic output feedback control, this zoom portion I had plotted. So we have for this design n equal to 5, t equal to 1 second, and delta is 0.2 second. Just a recall of values, a few slides earlier they were there. Now, because between two intervals, during one interval of length delta is some kl times ykt. So this is constant over the entire interval capital T, which is large, and depending upon this value of kl, the control signal changes. Now this is it. 1 second is somewhere here. This is 1, 2, 3, 4 and 5. So 1 second is here. This is 5 plus 1, 6 second, and similarly 7 second, 8 second, 9 second, and then 10 second. Now, because there are 5 different values for KL, for the same output which was collected here, the control signal is this, or this, or this, or this, or this. 5 different values of control signal are generated from the same sample of output, and this is what is basically there in the periodic output feedback control. For the same output signal collected at some time in instant kt, the input is k0 times ykt, k1 times ykt, etc. that is shown here. Means that input signal is not constant over the interval. That is the basic thing in the periodic output feedback control that is seen here. However, as the system come closer to equilibrium, these variations are smaller, and eventually they will become zero, because the control variable is brought to the equilibrium point. So any gain times that error will be 0 because error is 0. Now we see the responses for n equal to 8. I'm sorry, this is typing error. This is n equal to 8, and the set of gains k2. Now, as this was a bad design, you can see that input variation is much larger. It is minus 6 volt and plus 4 volt. In fact, if you can see from the previous slide, it was less than 1 volt on the negative side, less than 0.5 volt on the positive side. Here, because this design is not that optimized, it is more than minus 6 volt on one side and close to 4 volts on the other side. However, the system is stabilized even with the poor design. So this is how the voltage signal varies. This is how the control rod position varied. This is how the delta n varies. Of course, the control is better. It is brought to the equilibrium without any undershoot and faster. So this is how delta neutron density varied, delta eta. This is how the the voltage signal proportional to the neutron density varied, and this is how the rate signal varied. Now with the larger gains, the only problem is that the control voltage swing between some minimum and maximum was large, much large compared to that other gain which was smaller, and which is a point of concern, of course, in control design. We generally try to get control variations which are not so high. So that is why I was telling this is a bad design. Please remember, this is not n equal to 5, this is n equal to 8. Number of 8 sub-intervals during one output sampling interval of the system. This is finally again the zoomed over a smaller time. Earlier it was shown over a longer time. Zoomed variation of control signal. You can again see that it is k0 times the output, k1 times output, and so on. So for the same value of the output, there are different control signals which are applied over the different subintervals. So that is how the reactor behavior is, and how the reactor controller based on a periodic output feedback control principle is to be designed. Thank you very much. We will see the fast output sampling controller in our another lecture video. Thank you. See you again.